Swayam Prabha. Digital India. Educated India.
In this lecture, let us discuss about the basics of compressible Navier-Stokes equations. In the previous lecture, we looked at one dimensional Euler equations, and we are trying to extend it further now to 2 dimensions, and then we are also looking at the viscous situation now by invoking Navier-Stokes equations. We continue to discuss about the compressible form of Navier-Stokes equations, so that we have the ability of this set of equations to look at high speed flow problems and wave features which may emerge in such flow problems. Here we have written down the equations more thoroughly, not straight away in flux vector form, but later on we will also look at the flux vector forms, and you are going to use the flux vector forms only when we discuss about numerical scheme. So, this is the continuity equation first. Of course, we now have a y component included. Then the x momentum equation, again as you can notice in conservative form, because the del x, del y are operating on a set of terms. And you notice that, for example, the pressure gradient is not left on the other side of the equation, but taken to the left hand side. So, are the viscous terms along with the convective or advective terms, which are already there on the left hand side. And for each term, we have the partial derivative operator outside the expression. So, that is how the terms have been written. Of course, because it is viscous equations, you have the stresses, the viscous stresses which are now coming in, and you have the y momentum equation additionally. Now comes the energy equation, and since you are solving viscous flow, you are accounting for the heat transfer as well as the work done by shear stresses and normal stresses, and we are going to account them in the energy equation. We had defined the E t term already as the sum of the internal energy and kinetic energy per unit volume in the lecture on Euler equation. Here, because it is a 2 dimensional problem, you have both u and v contributing to the resultant velocity. And then you have the expressions for shear stresses and normal stresses. The normal stress terms include the lambda term, which from Stokes hypothesis is minus 2/3 mu. From Fourier's law, you are defining the q x and q y terms depending on the thermal conductivity and the temperature gradient along the respective directions. Now, if you look at the above equations carefully, we have in all 8 unknowns: density, 2 components of velocity, pressure, internal energy, temperature, the viscosity coefficient and thermal conductivity. Now, we essentially have 4 conservation equations which we can solve in order to compute these values, but since we are running short of equations, we cannot solve it at this point. So, how do we fill up the gap? Of course, we have to bring in more relations to model the behavior of the working fluid, let us say air, we bring in the perfect gas equation of state, and then we are not going to talk about very high temperature problems that we will solve with using these equations at this point at least, and therefore, we assume calorically perfect gas where Cp, Cv are essentially constants. They are not going to vary with temperature or pressure. Then we need a law for mu. How does mu change with temperature? So, the law essentially is going to express mu as a function of temperature along with certain constants which we can feed in the relation. So, we have the Sutherland's law of viscosity as a function of temperature, where mu naught, T naught are reference values at standard sea level conditions. So, once we fit them in, we just plug in the temperature on the right hand side, which can change from point to point in a compressible flow because of a very energetic nature of the flow. The temperature changes significantly. Once you feed that here, you get the value of mu as a function of T. What about mu? What about K? Let us see how we can work out K, the thermal conductivity. So, for that we invoke the equation for Prandtl number, mu Cp by K. We already discussed that mu will be worked out as a function of T. So, that can be plugged in here. We are assuming a calorically perfect gas, air. So, Cp will be a constant, and for calorically perfect air, Prandtl number can be taken roughly as 0.71. So, in the given situation, you can work out K as a function of T basically. So, now that you have 4 more relations, your system of equations is now closed. There are 8 unknowns and 8 supporting equations which can now be used for solving for the flow field. Having said that, let us now look at the conservative form of the compressible Navier-Stokes equations in 2D, for which we invoke the flux vector form, which we already learnt in the context of 1D Euler equations. The only additional term that we have over here is del f del y, but then there are more elements in u and e as well over here, and there are additionally viscous related terms, both in the sense of stress as well as heat conduction. So, having said that, we now see how u changes. So, there comes the additional term here due to the second component, and then you have more terms over here. This of course, is altogether new in comparison to 1D Euler, and then these are the additional terms in E, which is the flux vector along x, and now you additionally have a flux vector along y. And then if you were to solve for Euler equations, then you would not have had this term or these terms. So, these are the additional terms, the additional effects which come due to a viscous flow. Now, we are going to use a time marching technique to solve for the compressible Navier-Stokes equations. We are going to discuss about a possible numerical scheme to do that. So, we take the flux vector terms to the right hand side, and then we say that we want to progress the solution in time. So, in order to do that, we need a relation of this kind. So, we expand the u at the point I j. So, this is basically the spatial point, and the superscript is the time index. So, we want to take the solution from time t to time t plus delta t using a Taylor series expansion. We need an assessment of the time derivative of u in that case. So, we mark it as an average value multiplied with delta t, and we ignore the higher order terms. So, as long as delta t is really small, the higher order terms will not matter so much, hopefully. And the flow field variables in the u vector are either known from initial conditions or from the previous time step t. So, that we can take the solution to the next time step using a scheme like this. How do we define the average value of del u del t? We mark it like this. So, we try to take an arithmetic average of del u del t that we assess at the time t, and then we have another assessment of del u del t, which is what we call as a prediction, which we will discuss in due course. And we are going to follow a very famous technique, which is often called as the McCormack's time marching technique, in order to do these calculations. So, the McCormack's technique is basically a technique based on predictor corrector scheme. So, you do a prediction and then you correct it to finally reach your result at the next time step. That is the basic philosophy. So, what are the compute steps that we want to follow? Let us see. So, there is a prediction step or predictor step that we begin with, where the u bar value indicates the prediction. In order to proceed with that, let us see how we work out the del u del t over here, which is essential, because you know the value of u at time t already. You need to assess what this derivative should be at time t, so that you can do the prediction. So, how do we define that? We define it with a relation like this, where you can see that we have essentially used this equation and we have discretized each of these terms on the right hand side in order to get an assessment for del u del t at t. As far as taking the finite difference is concerned, we have taken forward spatial differencing. We already have learned about forward differencing. So, we are applying forward differencing here. Remember that E is a flux vector. So, it comprises of elements E1, U2, E3, E4 etc. So, when we write E in general, we are meaning that it applies for each one of the components of E. Similarly, for F. So, each component is forward differenced I plus 1 j minus I j at the same time t divided by delta x. So, this is of course, a first order accurate forward differencing. The same applies for F. Remember that F is the flux vector along the y direction, and therefore, over here the forward differencing is along the y direction. So, the j index changes, the I remains fixed. Here the I index changed while j remained fixed. So, that is how by using forward spatial differencing we assess del u del t. Once we do that, we are able to work out this, the u bar, which is called as the predictor step. All right. So, this is the prediction we have done now. Now, we have to correct it. We are not very sure whether that is an appropriate value. For doing a correction, before we move on to that correction step, we also have to do something more. Based on the u bar value that you have predicted, you update the E and F vectors and obtain the values of E bar and F bar vectors as well. That means, based on the prediction that you have done for the flux vector of conserved variables, you also do the prediction of the flux vectors E and F. Once you do that, you go to the next step. You want to do a prediction of del u bar del t at t plus delta t. How do we do that? We apply backward differencing here. So, in the earlier step we had done a forward differencing, here we apply a backward differencing. So, we are differencing the other way I j minus I minus 1 j. I j minus I j minus 1. So, notice the directions. So, both along x and y we are using the backward directions. So, that helps us to assess this. Remember that this step is very important to get the E bar and F bar values, because those are the ones which are using here for the differencing. So, now what do we have? We have two equations A and B. A was obtained by using forward spatial differencing, B was obtained by applying a backward spatial differencing, and now we are going to combine the two. So, when we combine A and B, we end up getting a second order accurate corrected value. Note that both of these individually were first order accurate, but when you combine them they are going to give you second order accuracy. We are not getting into the mathematical aspects by means of which you can prove the second order accuracy, but that can be left as a homework for you, which you can explore in due course. Finally, with the del u bar del t value that you have assessed, you sum it with del u del t which you had assessed in this step, take an arithmetic average, and that is what gives you the del u del t average value, and that is what you fit into this equation which you got from the Taylor series expansion in order to move the solution to the next time step. So, that is how the prediction and the correction is done in the two sub steps in order to move the solution to the new time step. After each predictor or corrector step, the primitive variables are obtained by decoding the u vector. We have seen earlier, even in the context of Euler equations, that we define different components of the conserved variables vector as u1, u2, u3, u4. So, in 1D Euler equation there were only 3 components, here there is an additional component. So, you have u1, u2, u3, u4, and now density is u1, velocity along x direction is u2 by u1, along y direction is u3 by u1, the Et can be set as u4, and then the internal energy comes out to be an expression like this, where again u2 again u square comes from u2 by u1 whole square, or v square comes from u3 by u1 whole square, and so on. That means, in each one of these expressions from the 4 components of u, you can finally express each one of these primitive variables. Similarly, once you have worked out density and 2 components of velocity E t and E, you can get pressure, for example, temperature, viscosity and thermal conductivity. For temperature, what do? We divide E by C V. So, C V we are assuming a calorically perfect gas. So, C V is a constant. E you have already got from this step. So, you can obtain T. You already got density and temperature. So, you can plug them in here, you get pressure. Once you get temperature, you can work out mu from the Sutherland's law, and from the Prandtl number equation you can work out the value of thermal conductivity, which will come out to be a function of temperature. So, that way each of these 8 unknowns can be updated at every predictor or corrector step, which needs to be done carefully. Now, with whatever we have learned up to this, we can think about a simple problem for which we can develop a simple computer program at home. We do not have enough time to discuss all the details of the computer programming here, but we will just discuss about the broad framework. Let us set a problem like this, that we want to have a supersonic flow impinging on a flat plate. So, it is moving parallel to the flat plate, and we are going to solve 2D compressible Navier Stokes equations in order to generate the viscous solution that develops when that supersonic flow moves past this flat plate. Now, because it is viscous, as you can understand, obviously there will be a boundary layer formation on the flat plate, irrespective of whatever Mach number it is. And the boundary layer thickness delta also has an accompanying displacement thickness, right. So, that displacement thickness is usually smaller than delta, but nevertheless it will be there, and that will give a slightly inflated shape to the flat surface, which means the flow will get compressed to some extent, and therefore, there will be a formation of a weak shock, because you have a supersonic flow impinging on the surface, moving parallel to the surface. So, this shock will be an attached curved shock. Why curved? Because the displacement thickness is changing along the flow direction. It is a function of x. So, delta star is a function of x, and it is not going to be a straight line indicative of this growth, and therefore, it is not as simple as flow past a wedge like surface, in which case you would have had a straight oblique shock. But because delta is not going to, delta star will not appear like an inclined straight line, there will be a curved shock. Let us try to define a numerical domain such that the shock can be passed through the outflow of the domain. So, the supersonic flow comes into the numerical domain through the inflow, moves out through the outflow, and then it should be able to capture the boundary layer effect and the attached curve shock as it moves. This we will call as far field, as long as we keep it quite some distance away from the plate in terms of the boundary layer thickness. So, the diagram shows that it is about 8 to 10 times larger a distance than the boundary layer thickness, maximum value of boundary layer thickness, which is towards the outflow plane of the problem. You can call this as a far field, and the conditions over there would be very similar to that you have at the inflow. At the inflow, what do you have? You have u equal to u infinity. And how do you obtain u infinity? So, from the Mach number you have u by A, and from the temperature that you have set in the free stream you can define A, and based on the Mach number that you have set, u will be automatically obtained. So, that will be assigned as u infinity, v will be 0 because the flow is parallel to the x axis, and then you can set the values for pressure and temperature. You should be able to work out the rest, and of course, you apply the simplifications that we have already discussed about, that it is a calorically perfect gas. We are not going to use a very high supersonic Mach number, which brings in conditions which are hypersonic in nature, but it could be a fairly high supersonic Mach number, so that the thermal effects in the flow also become perceivable. That means, there is viscous dissipation in the boundary layer, which shows up in the heating of the boundary layer region and so on. That brings us to conditions at the wall. At the wall, of course, by virtue of the free stream u equal to v equal to 0, we impose normal pressure gradient equal to 0, which defines the pressure at the wall. A second order accurate expression for the pressure at the wall would be like this. Let us try to explain what we mean by this expression. So, this is a finite difference representation of del p del y equal to 0 condition. Try to explore yourself how this can be obtained. This is basically a second order one sided differencing of the first order derivative. If you have a point here on the wall, the next point here, still the next point here and so on, you can call this as P I 1, this as P I 2, this as P I 3, and then the P I 1, that means the pressure at the wall gets defined based on the pressure of the two neighboring points in the flow field. And because the pressure in the flow field will be obtainable by using the conservation equations, they can help you define the pressure at the wall using this relation. Let us set some fixed temperature at the wall, in which case it is called as an isothermal wall. On the other hand, if you apply the condition that del T del y equal to 0 at the wall, what you have is an adiabatic wall, and then you would actually have to invoke a condition like this for temperature, in which case the temperature at the wall will also be solved and updated as the solution progresses. And this is how you can progress with the solution by updating values at the walls. As far as velocity is concerned, that of course remains 0. How about the outflow? In the outflow region, we generally extrapolate the conditions from the inner region of the flow. So, in the outflow, we have to invoke information from inner points like this, and let us say if you want to extrapolate the u value, you can write an expression like this, very similar to what we did for pressure at the wall. Where I max is the maximum value of the I index that you have used. This corner point, for example, would have an index of I max, J max. So, J max is the maximum number of grid points along the y direction. As you can understand, here you have just extrapolated the value at the outflow based on internal values by setting the condition del u del x equal to 0. Similar relations can be applied for V, P and T, and that is how you can solve them. Whatever you have imposed in the inflow can as well be imposed in the far field. At the corner here, you have to impose the no slip condition, but then you can retain the pressure and temperature as free stream values. At this corner again it continues to remain as a no slip corner point, but then pressure, temperature etc. can be part of the outflow calculations or part of the wall calculations. So, that is how you should be able to solve this problem. You take domain dimensions in a manner that the Reynolds number is restricted to a few thousand. So, that we are essentially computing a laminar flow, and for deciding the time step you can go in for the CFL criterion, but usually there is a slightly more advanced version of the CFL criterion is available, because we have to account for 2D effect as well as viscous effects. So, try to explore how you can apply a suitable CFL criterion for choosing the delta t, because you are going to time step the solution. So, you need to have an assessment of delta t. If you are able to put a computer code in place for this problem and you find that it is not working for the delta t that you have chosen and the rest of the coding is all fine, then try to reduce the delta t till the problem starts getting solved, and you finally come up with a nice solution of the boundary layer solution as well as an attached curve shock, which will be really very exciting. These are some of the references which could be of use to you. They are very nice extensive books on different aspects of CFD. So, in this lecture we discussed about basics of compressible Navier-Stokes equations, and we also discussed about a numerical scheme for solving it, which you can use for attempting a comparatively simple problem of 2D compressible boundary layer on a flat plate. Thank you.